Here we will discuss the braking methods of induction motors. This is the part 3 of module 4. The popular methods for braking of induction motors are regenerative braking, plugging and dynamic braking. Among these we will be discussing regenerative braking and plugging. First of all, we will discuss regenerative braking. Regenerative braking is nothing but reversing the power flow. That is, power will be flowing from load to source. That means the regenerated power or the power regenerated during braking will be utilized by some other load connected to the same power supply. Let's see how it happens. The power input to a three-phase induction motor is given by Pn is equal to 3 into Vs Is cos phi s, where Vs is the stator input voltage and Is is the stator current and phi s is the phase angle between Vs and Is. If the machine is operating in motoring mode, the polarity or sign of Pin will be positive. That means if the motor is working in the motoring mode, that is in the first quadrant, then Pin will be positive. For Pin to be positive, the value of cos phi s should be positive. For if in order to keep cos phi s as positive, the value of phi s should be less than 90. That means for motoring operation, the value of phi s will be less than 90 degree. Now let's see how the operation is shifted to the second quadrant, that is regenerative braking. When the motor speed omega m is greater than omega ms. Consider a particular case when the motor speed is greater than the synchronous speed. Then the value of slip S is equal to omega ms minus omega m by omega ms. This is the equation for slip. In this equation, if omega ms is smaller than omega m, then this term or the slip will become negative. If slip becomes negative, then the value of the rotor induced EMF as well as rotor current will be reversed. That means if slip is negative, then rotor induced EMF and rotor current will be reversed. At the same time, the component of stator current which balances the rotor current will also reverse. This causes the value of phi s to become greater than 90 degree. That means if slip S is negative, phi s becomes greater than 90 degree, and if phi s is greater than 90 degree, cos phi s will become negative, so Pn will become negative. Input power Pn will become negative. That means the flow of power will be from load to source. If it happens, then it will be regenerative braking. Thus, regenerative braking is achieved. Note the point, it happens when omega m, that means motor speed, is greater than synchronous speed. For this to achieve, we have two different methods. Either we have to use a variable frequency supply. If we are using a variable frequency supply, then if you have to reduce the speed or if you have to brake the machine, using regenerative braking, then frequency is to be reduced. supply frequency is to be reduced. When supply frequency is reduced, omega ms becomes smaller than omega m. That is one possibility. Otherwise, we will have to use a constant frequency supply. Then the speed control or regenerative braking is achieved only above synchronous speed. That is, omega m should be greater than synchronous speed in order to achieve regenerative braking. That we will discuss later. And this is the speed torque characteristics of regenerative braking. The dotted line is shown for motoring, that is first quadrant. So normally the motor will be operating in the first quadrant, and in order to brake the machine, we have to bring the machine to the second quadrant. So when the second quadrant operation, you can see that it is possible only above synchronous speed. This is equal to omega ms, that is synchronous speed. Below synchronous speed it is motoring. Above synchronous speed it is regenerative braking. This is what we have already discussed. When it is fed from a fixed frequency source, regenerative braking is possible only for speeds greater than synchronous speed. With a variable frequency source, it can also be obtained for speeds below synchronous speed. The advantage of regenerative braking method is the generated power is usefully employed. It's used somewhere. But the disadvantage is when fed from a constant frequency source, it cannot be employed below synchronous speed. Normally the machine will be operating below synchronous speed, and we have to brake the machine below synchronous speed, and that is not possible with a constant frequency source. So we have to employ a variable frequency power supply for this. Next is plugging or reverse voltage braking. Plugging is nothing but reversing of phase sequence. In the case of a three-phase induction motor, when the phase sequence of the supply is reversed, the operation shifts from motoring to plugging. The phase sequence, how the phase sequence is reversed? It is by interchanging the connections of any two phases of stator with respect to power supply terminals. So, among the three phases R, Y, B, any two phases are interchanged, then the machine will suddenly shift to plugging or plugging or reverse voltage braking. During plugging, let's see how the plugging happens. During plugging, since the phase sequence is reversed, the direction of rotating magnetic field also reverses. So if the direction of rotating magnetic field reverses, the value of omega ms becomes minus omega ms, because omega ms is the speed of rotating magnetic field. So it becomes minus omega ms. Then the slip during plugging, Sn is equal to minus of omega ms minus omega m divided by minus omega ms. So by rearranging the terms, we will get 2 minus s, where s is equal to omega ms minus omega m by omega ms. So this is the equation for slip during plugging. So we can see that the value of slip during plugging may go up to 2. The maximum value of slip during plugging is 2. Then let's see the torque speed characteristics. We will discuss this in detail. This is the motoring operation, as we have already seen. During motoring, let's assume that this is the operating point when plugging is applied. At this operating point, when plugging is applied, the machine suddenly shifts to second quadrant. It will reach this point and gradually its speed is reduced. and suddenly it reaches 0. So at the instant of switch over to plugging, the slip can be go up to 2, that we have already seen from the equation. So the rotor induced voltage can be twice of its value at 0 speed. The slip is a measure of the rotor induced EMF. How much EMF will be induced in rotor, because it indicates the relative speed between the rotor and the rotating magnetic field. So it will the slip will indicate how much EMF will be induced in the rotor. So since the slip can be go up to 2, the rotor induced voltage can be twice that of the value at 0 speed. So the motor current also becomes very large, although the braking torque is low. So this is not a desirable thing when the machine is undergoing braking. The braking current becomes very large. That means the machine may get damaged due to overheating. So in order to prevent the flow of high motor current, we can insert some resistance in rotor circuit if it is a slip ring induction motor. So in the case of wound rotor or slip ring induction motor, a resistance equal to twice that of the starter resistance is inserted in the rotor to limit the braking current to starting value. So it also increases the braking torque. So here the curve 1 indicates the characteristics without adding any external resistance. So here you can see the torque, braking torque is small. When we added an additional resistance with external resistance, the braking torque has becomes large. The torque is not 0 at 0 speed. You can see in both the cases, when the speed becomes 0, the torque is not equal to 0. Here the torque, there is a definite value of torque. Here also there is a definite value of torque. That means even though the machine it has stopped, that means the machine has reached its 0 speed. From initially it was running in the forward direction. Now the speed has reduced, gradually reduced, and it has reached a 0 speed. But it doesn't mean that it will stop. It will start rotating in the reverse direction due to the presence of this negative torque. So in order to prevent that, we have to switch off the power supply before it reaches 0 speed. That means at very near to this point or this point, we have to disconnect the power supply. So that's what is mentioned in this point. The torque is not equal to 0 at 0 speed. So it is necessary that the motor should be disconnected from supply at or near 0 speed. And one more thing to be noted is that during motoring, the characteristics is like this. That is in the first quadrant. And during the third quadrant, it is also a motoring, a reverse motoring is happening in the third quadrant. So the curve will be very much similar to that of first quadrant. Reversed cara will be there. So during plugging, the characteristics during plugging will be an extension of the cara of third quadrant. So during plugging, the characteristics will be an extension of the characteristics of third quadrant. Thank you.